In this eighth lecture, we shall consider the integration of Fourier series term by term. Let us consider a function f of x which satisfies Dirichlet's condition in AB so that delta is equal to b minus a. Then we can expand f of x in Fourier series as a0 by 2 plus summation over n is equal to 1 to infinity a n cos of 2n pi x delta plus bn sine of 2n pi x by delta. We make it short as a0 by 2 plus summation over n for we write this is as a n to the power minus p. This is for a n and this is cos of alpha n x, then b n to the power minus q sine of alpha n x. Now, what we have used, that we have seen that a n is a upon n to the power p, a upon n to the power p, and bn is equal to b upon n to the power q, with p and q are greater than equal to 1, and we have used alpha is equal to 2 pi upon delta. So this is the simplified form. If we integrate this, between 0 to x dx, then we will have f of x dx from 0 to x. This is x, 0 to x, and on this we will have half a0x. And now coming to this term, we will have n an x integration of this term, and then we will have minus b by n to the power q plus 1, and we will have sine term. So the integrated if we evaluate this sum, say this is f of x is x, then we get half of x square on the left, and on the right we will have to perform this summation. That is, we have integrated the right hand side term by term. It is found that the power of n in the denominator is increased by 1 on integration. That is, if we have originally the variation as n a to the power n, then upon integration this becomes a to the power n plus 1, a to the power n square. So the rate of convergence of the series on the right is faster for this case rather than this. So on integration we get a series on the right hand side which has a faster rate of convergence compared to the original series. So the term by term integration of Fourier series of a Fourier expansion always leads to a correct result. We shall consider this in few cases. So let me first write few simple expansion that we have already carried out in an earlier lecture. First is that f1 of x is equal to x is equal to 2c by pi integration a then the second function f2 of x is equal to x square c square by 3 plus 4c square by pi c square upon pi square and finally we consider f3 of x is equal to x cube, and this expansion is 2c cube by pi 2c cube by pi summation over n minus 1 to the power n plus 1 by n plus 6 n to the power n cube pi square this expansion we have already done in this class. All this function has been expanded in this range and assumed to be periodic. Now let me first integrate the f1 function. We integrate this between 0 to x dx. So we get integration x dx from 0 to x. Then we will have 2c pi if we integrate sine we will have minus c upon n pi, and then the result is let me first write the basic step. Sine of n pi x c dx from 0 to x. So this is equal to 2c by pi summation and then integration of these will leave minus c by n pi cos of n pi x c minus 1. This is from the lower limit 0. So altogether we will have this minus n makes it and c. So this is 2c square by pi square. This pi is taken out and then summation over minus 1 to the power n upon n square multiplied by cos of n pi x c minus 1. Now on the left hand side it is half x square. This is half x square. So we will have, if we multiply this half with this, we have x square is equal to 4c square pi square, 4c square pi square. Then we will have summation over n minus 1 to the power n, n square cos of n pi x by c, and the term is plus this is the result. If we compare it, then let me first evaluate this term. If we place in F2, if we consider F2 with x is equal to c, it gives you c square on the left, then c square by 3, then 4c square pi square, 4c square pi square, and then we will have minus 1 to the power n square and cos of n pi. This is equal to minus 1 to the power n. So no, that will not work. I have to find out x is equal to 0. No, this will not work. Let me think a bit. This leads to Riemann zeta, but we are not interested in Riemann zeta. This leads to that summation over 1 by n square is equal to pi square by 6. We are not interested in this result. We are trying to get this part out. So we put x is equal to 0 in this case in F2, and we will have on the left hand side 0 is equal to c square upon 3 is plus 4c square pi square, and then we will have minus 1 to the power n square, and cos of 0 is 1. So 4 by pi 4 upon pi square and minus 1 to the power n plus 1 by n square is equal to 1/3, or summation over n is equal to n plus 1 by n square is equal to pi square by 12. This part is pi square by 12. So this is pi square by 12. So we will have 4c square pi square summation over n minus 1 to the power n square cos of n pi x by c plus 4c square by pi square into pi square by 12. So this part becomes c square by 3. So we write it as, if we write this term first, c square by 3 plus 4c square pi square this is exactly F2 we have listed above. So the left hand side and right hand side are the same. That is, we see that the term by term integration of Fourier series leads to a correct result. We shall consider one more example of this category. Now we integrate F2. We integrate F2 and see what happens. So we integrate F2. So we will have x squared dx from 0 to x. On the right hand side we have 2c cube by pi summation over n minus 1 to the power n plus 1 by n plus 6 minus 1 to the power n cube pi square, and then we will have integration of sine of n. I am integrating f2. We should write the expression for f2. So this is c square by 3 times integration of this x plus 4c square pi square zero to x. Now this is c square by 3x, and this is on the integration c will come, so this will make c cube, and 1 pi will come, that will make pi cube. 4 c cube pi cube, and then we will have summation over n minus 1 to the power n cube, and cos is integrated, so sine, and in the lower limit it is 0, sine of n pi x by c. For x we use this result, so we get 3x cube is equal to c square by 3, and for x we write 2c by pi so we have x replaced c by f1. Note that f1 is equal to x has been replaced, and then we have the original term. If we multiply this all through by 3, we will have x cube on the left, and on the right hand side we will have 2c cube pi and if we multiply this 3 by, it will be 12 c cube pi cube. We take 2c cube by pi common, from this term 6 minus 1 to the power n cube pi square you see this is nothing but f3. So we have taken two simple examples which shows that if we integrate the Fourier series Fourier expansion on the right, term by term, then we get the correct result. In the next class we shall consider the differentiation of Fourier series.